Yeah, thank you very much. Welcome to my talk about some of the internals of the Django ORM. I've had that quote on my last talk at PyCon in Germany in April by Andrew Godwin. The ORM is the majority of Django. So that's true here even more, because we are going to have a look in the inner mechanics of query set, query managers, as you will see. But first, let me introduce myself. So my name is Bas. So my real name is Sebastian Steins. I'm a German living in the Netherlands. And for my Dutch friends, I go by Bas. For my German friends, I go by Sebi. I'm currently working for a company called Miltenyi Biotech, and there we produce devices for lab devices for blood cell analysis, and there's a lot of biological and physical knowledge in there, and my role is actually to teach Python to these biologists and physicists. I've been programming since the age of 14, using Django since 2008, 3 years after its inception, which makes Django already kind of a boring technology, which I would consider as a good thing. So what can we expect from this talk? So we will go through the call chain from manager to SQL compiler. We will see how laziness works inside the ORM. And we will see how the ORM manages what is called where nodes. So these are the trees in which complicated filter expressions live. And at the end, we will have a short look at database side views. So a little word of caution here. The class structures I show here, they are not officially documented. And the direct use of some of the methods I will show you is discouraged. And that is for basically two reasons. First is the architecture of these classes is so well designed that you can easily hack everything you want via publicly documented APIs, such as managers or unmanaged models, as we will see later. And second is, especially with regard to the ongoing work on async ORM, these classes might change over time without further notice. So anyway, we are curious to see how it's working, so just be warned, but follow me along. So we start with a very, very simple set of models. Actually, we only use the block model here, and this should already look familiar to any one of you. So, and then we have basically the hello world query of Django ORM, which is just the select star without further where clause. But we can try to deconstruct it. So what do we have here? So first of all, we have blog, capital B, singular, which is our model. And then we have objects, which is our manager, which is implicitly created by Django's ORM when we define the model. And then we have all. This is basically, again, select star without further filter. And all of this gives you a query set, which is then stored in blocks, lowercase b, plural. That's what it is about. So from this very simple query, you can already deduct some design goals of Django's ORM. There are no SQL-like words. So, I mean, we have filter, but we don't have where. There are also no SQL strings, like partial queries or something like that, which you might have seen in other ORM frameworks such as Hibernate or the like. But merely all of what we do here, all of how we interact with the ORM is just by using pure Python function calls. So, and the call chain, so basically from your intention to get to some objects to actually hitting the database, these are the classes which play a role in that game. So we start with the manager. The manager creates a query set, and the query set creates a query, and that query is passed to a SQL compiler class, which eventually then puts out the string, select blah blah, from where, and so on. So what the SQL compiler now does is, I copied the doc string of the original method. It gets you an expression, the SQL with params and an alias. And we will see what the alias is about in a couple of minutes. So what it needs is the base model of the query. That's logical, because from the meta class of the model it can deduct the base table. It can determine the order of the columns in the model. This is also relevant because the result sets from the database will come in a enumerated way and not in a hashed way like in a dictionary. And then we have related class infos, which are mostly for compiling joins. So this is how it looked like if you really looked into the internal attributes of that query class. So you might have already used the qs.query alongside with print. So that gives you the actual SQL statement. But this is, okay, in this case it's cached. But on the way how it is compiled is there are a couple of instance variables which are quite important for it. First one is alias map. Alias map actually is a dictionary with the table name as a key, pointing to a data structure called base table to reference the actual table. So then there is the alias ref count. This is important. This is set here to 0 because we start counting at 0 as always. But it would increase to 1, 2, 3 if we add additional joined tables into our lookup. So this is automatically increased then. And then we have the base table, which is actually derived from the model's meta class. In our case, it's demo_blog. So even if we have seen the SQL query here, that does not mean that we have hit the database at all. So what makes a lazy ORM start doing its work? Or in other words, unless you, as long as you don't call specific methods, the DB is not hit at all. And we will now have a look at what these specific methods are. So most of the time you can chain more methods to a query set, like adding other filters, adding other exclude statements, and the like. But still, this does nothing with the database. Instead, it would just return a clone of that original query set with the additional filters applied. So, and these special methods that triggers the execution are most of the time special Python dunder methods, like think double underscore. So for example, the query set implements an __iter__ method. this one is basically used when you write something like for block in QS in your code. Same goes for __len__, which gives you the count, not the SQL count, but the actual instances count of your query set. And there is also get item, which allows us to basically limit the number of returned records. So that's basically Django's way to implement different limit implementations for different database vendors. So now the question is, what if we add filters? Like if we don't write blocks.objects.all, but blocks.objects.filter, and then put some keyword arguments in there. So what happens is, whether we write filter or exclude, both of that ends up in a method called _filter or exclude in place in the query set class. So what happens here is everything you put in your filter method ends up as a regular queue object. And these queue objects are very well documented. So there are a couple of advantages here to do it that way. The first one is the query set class itself that doesn't have a special case for filter or exclude. It just handles queue objects all the time. The second advantage is that when you are dealing with queue objects anyway, you can customize your query very easily with well-defined and publicly documented APIs of that queue objects. So the takeaway here is that filter and exclude are just abstractions on the queue objects, which are then used internally. So out of these queue objects, the Django ORM will build something which is called a where node, which is actually can be seen as a tree, and it is stored in the instance variable where of the query set's query, like blocks.query.where, will give us something like this if we apply just like this simple filter. So what now if we add a more complex filter? So for example, we want to have anything starting with A or having the ID of 1. So this gives you like a structure which actually looks like that. It has AND, OR, exact, call, demo block. It looks like, so you don't have to recognize that immediately, but if you have a look at it, you will recognize how these things are coming together. But the whole thing looks a lot like a Lisp source code, with all the brackets around and stuff like that. So what happens here is you have combined two filters, one exact filter and one I starts with filter with an OR. So that's what the OR is for. But what is the AND for? Any idea? What is the first AND for in that where node? There were two. Yeah, exactly. That is just, if you will, a preparation for the next change filter to come. So the next filter will be added with an AND. And this is really how it works. This is the original source code of the method that will add the queue object to the where node. There's a bunch of stuff we can't cover here now for brevity reasons, especially when it comes to joins. But what you see here is there is a connector and that is exactly what you said. That is the end connector for the next query. And it figures out if I have a branch in my node or in my tree which is negated or which is not negated. And based on these branches, I do a tree traversal with that simple for loop here, and I end up with very complex where node tree objects. So, one practical example, now that we have a little understanding of the inner mechanics, and that is something I've really seen in production level code, is, now well, you have a model, and this model is obviously attached to a database table, but for some reason, maybe performance or whatever, the same information of that model is stored inside a view in the database. So what the idea was here is, well, I want to query the view for my read access, but what I want to get back from my ORM is still the original object. So how could we do that? Any idea? That's the better option. Yeah, abstract models, unmanaged models, yeah, that's certainly the better option. But I showed you the worse option first. We can monkey patch the query object. So as I told you, there is alias map, alias ref count, table map, and base table. And I can just overwrite it, change the behavior of the SQL compiler eventually that way, but still end up with an instance of my block and not of my second block or anything else. And now, yes, there is a better and more obvious way to do that by leveraging unmanaged models. I can just inherit from the model I wanted to query, set the meta options managed to false, and specify the database table I really want to query, which in that case would then be a view. So now that we have get our intention to seek data from the database, brought it all down to the database, now the question is how it comes back. So what steps are taken to get the results from the database, and then on the way back create create a model instance for us. So, and this is pretty straightforward actually. There is in QueryPy that model iterable, and it just takes the results the compiler has given us and instantiates like our model class. So, and here now you know why all these internal mapping fields have like numeric values attached to it, is because the database doesn't give you like a dictionary back, but a list, and you have somehow to have a correspondence between the name of a field and the actual position of that field, and that is here in that list comprehension done. So then final word about managers. No, not that one. But managers in general. The recap of the class architecture I just showed you is manager creates a query set, creates a query, and finally it goes down to the SQL compiler. So each of these classes add one layer of abstraction to my whole query, or to my whole intention. And almost every need you might have for custom queries can be met by writing a custom manager, because the custom manager, you have access to all of the underlying mechanics, so you can just do that inside your manager. And as a short example, this is again like a very trivial one, the hello world of ORM managers is, say you have, you want to implement a soft delete model, which is whenever someone deletes something, you don't want to drop it from your database, but instead you set a flag, deleted, and when you read it, you just don't want to have everything which is marked deleted. So of course, there might be GDPR issues here, but that's another story. So what you do is, you just add a deleted field to your model, or any other field which can indicate a status, and then you get another manager for that object. I created a block manager, and what that manager does is it overrides the getQuerySet method. But it doesn't really just override it, but rather it gets the original query set from the built-in manager and then chains another filter call to it. In that case, filter everything deleted equals false. So what does that mean in consequence is that whenever you now write block.objects, .filter, .all, .get, whatever, you will never be able to access these deleted things again, and that is why, because in that case, this particular manager, you have given the name objects, which is the default name for managers in Django ORM. So if you want to have access to both deleted and undeleted, you would just have to give it another name. So I just heard we have a couple of minutes left. I try to cover almost everything here. Thank you for listening. We might still have a little room for questions.
Yeah. Yes, I think we can do one, maybe two questions. So please raise your hand if you have a question.
Over there.
You are in the front.
I don't know. I want the hard question about deep into the query. Hard question is, at first you show how you use query, but in this query you can use for class join class and for class where class you can define the complex filter. You can define more complex filter than in normal ORM. This is a big difference. And if I have complex query, what is better? To use row query, or I should use undocumented query joins and query there and query extra there classes? What do you think about it?
Okay, if I got the question right, it is about the more complex stuff which QuerySet doesn't give you access to. So the question is, do I use like the query class like I showed you here, or instead a raw query? Well, I would go for the raw query because it's documented and it seems more stable in its implementation. But I know there is not, that's maybe one of the questions where there is no silver bullet for all. And I remember our last discussion, so that's something perfectly fit for the coffee break.